So welcome everyone to TCS Plus, to the first talk of 2016. The operator for today's talk is Adit Ragev, and we also have assisting with TCS Plus are Thomas Bidek, Thomas Hollenstein, G. Kamat, and Clement Canon. Now Adit will go around the table introducing the groups.
Okay, let me try. We have a record high turnout today, so let's see if I remember all the groups. So first I welcome the group from Berkeley, headed by Brian O'Gorman. Hi, Berkeley.
Hi.
Let's see. Yeah. Okay, now we can hear you. Great.
Okay.
And switch to Clement Canon from the group from Columbia. Hi, guys in Columbia. And we have the group from NYU, Hug Bennett and others, a few floors above me. Yo Briette from CWI. Hi, guys. Kaveh Hosseini from UCSD. Hi, guys from San Diego. Seems like you again have nice weather. I envy you. We have Naihui leading the group from Penn State. And we have Ola Svensson from EPFL, Lausanne. Hi, everyone.
Hi.
Oh, great quality. So see from there. And we have Thomas Vidik, of course, joining us from Caltech. Hi, guys. Looks tasty. And we have finally Yi Jun Chang from Michigan. Hi, guys.
Hi.
Okay, now it's back to you in India.
Thanks for it. So just to remind everyone, we will be going around. So if you have a question during the talk, please unmute yourselves and ask the question. We encourage questions. The next talk, the next scheduled talk is by Ilya Rastenstein 2 weeks from now, and 2 weeks from then, so 4 weeks from now, will be Ronit Rubenfeld. So today's speaker is Scott Aaronson. And Scott is one of those people who needs no introduction. We have a record turnout today. But just a few words. So Scott graduated from Berkeley, and since 2006 or 2007, he has been a professor at MIT. Scott is, of course, known for his several breakthroughs in quantum computing, quantum query complexity, and so on. He has received a number of awards for this, including the Alan Waterman Award. And he's, of course, also known for his popularization of theoretical computer science. He's the zookeeper of Complexity Zoo, and he is the author of the blog Shtetl Optimized. Did I pronounce it correctly? I took a lesson from a dead, but it's already messed up. So Scott today is going to talk about quantum query complexity, the recent series of breakthroughs in quantum query complexity. We're delighted to have Scott. Welcome.
Yeah. Well, thank you. So this is my second time, I think, talking in TCS Plus. Good to be here. I mean, when they invite you for this thing, you can't exactly decline because, you can't travel. So, always good to, and by the way, please interrupt if you have questions because I can't actually see you. So the only way that I'm going to get any feedback is if you ask me questions. So, all right, great. So I wanted to tell you a little bit about the largest possible quantum speedups compared to classical computing, and so the overarching goal for me is what's sometimes being referred to these days as quantum supremacy, which basically just means your goal is to find some task, any task that that you can do with a quantum computer faster than you can do it classically. Okay, you don't care if the task is useful. You don't care, what specifically it is. You just want clear evidence for some separation. Now, I should tell you that personally, I sort of regard this as the #1 application of quantum computing. I mean, people talk about how quantum computers would be useful for factoring numbers and thereby reading people's email. They'd be useful for Grover search, potentially for some other things, machine learning and so on. Often I'll tell people that the biggest application of a quantum computer would be the one that's sort of so obvious that we barely even talk about it, and that's just simulating quantum mechanics itself. Okay, but the truth is that even bigger than that application, I think, is the application of just disproving the people who say that quantum computing is not possible. Okay, that's for me, all of the other applications are just sort of icing. What I want is to prove that that nature really does, put this computational power at our disposal. That quantum mechanics actually continues to be true, in the relevant regime. Of course, if it's not true, then that would be a discovery that would overturn a lot of what we think we know about quantum mechanics. And that would be one of the the biggest breakthroughs in physics, I think. So that would be even more exciting. Okay, but either way, I would just like to know, is quantum computing possible or not? And and I view this as a really fantastic goal, for the field for, let's say, the next 5 years or so. It is something that bridges a lot of fascinating theory that we're able to do today with a lot of experimental devices that we expect are actually going to be available within the next 5 years or so. We don't expect that in 5 years we're going to have fully fault-tolerant, error-corrected universal quantum computers that can run Shor's algorithm. However, we might have devices that can do something that's hard to simulate classically, and I think that that's an incredible milestone to aim for the field. But of course, the main work here is the experimentalists to actually achieve this. In superconducting qubits and ion traps or whatever. But the theorists have a crucial role to play as well, because we need to figure out, well, what is actually hard for a classical computer, among the things that a quantum computer can do. How confident are we that these tasks are hard for a classical computer? If we have these devices, what exactly should we do with them? What are the tasks that give you the clearest or the best quantum versus classical separation? Okay, now, as it happens, there were some very exciting results just within the last year about exactly those sorts of questions, and I'll touch on those in my talk. Okay, but let me start by sort of telling you 3 general principles that I think that I would advocate. Once you take this quantum supremacy, rather than solving a practical problem as sort of your goal for experiments. So all right. Well, the first is just the restatement of that. That eventually, of course, we would like to do things of practical use. But what I regard as sort of a prerequisite to that is just show that we can get a quantum speed up at all. Right? I would rather have a quantum speed up for something useless, but which I'm confident about, than an experiment that does something useful, but that we don't know whether quantum mechanics is actually playing a role in letting us do the thing faster. Okay, because it's like if you're trying to build a useful airplane, right? It's better to start with a useless airplane than with a very useful car, right? Okay. Now the second principle is that we need a clearly defined computational problem. Okay, so the way I like to put it is, what number am I thinking of right now is not a computational problem, right? Because it involves it's not well specified enough. It involves a physical system, namely me, which you don't know the mathematical details of. Okay, so there has to be some problem, like calculate the transition amplitude for this quantum circuit, which I will fully describe to you, right? And of course, it's wouldn't be surprising if a system that mimics that quantum circuit would do a very good job of solving that problem. that's fine. We can define a problem, around the physical system that we have that can solve it. Okay, but the classical skeptic has to be given a fighting chance. They have to be given a complete mathematical description of what it is that they need to simulate or do. Okay, so you can't just define your problem to be simulate my experiment or simulate a D-wave computer or something like that without mathematically specifying it. Okay, what are the inputs, what are the outputs, and what's the relationship between them. And then my third principle is that asking what is the evidence that your problem is hard for a classical computer is not just some side question. That's really the core of the entire issue, right? It's there are I mean, that may sound obvious, but there is there have been so many announcements in in the 20-year history of quantum computing that say, well, we can do such and such with a quantum computer, and that just sort of fail to ask the follow-up question, well, could you have done the same thing with a classical computer, in the same amount of time or even faster, and that's in particular, we want to see a separation between what you could do with a quantum computer and what you could do with a classical computer with a random number generator, right? Which we don't think of as quantum mechanical, even if it's a quantum random number generator. So in some sense, the counterintuitively, the major issue here is often not what the quantum computer can do. Often, that's the relatively easy part. Often the hard part, at least for theorists, is figuring out what a classical computer could not do, and on what grounds we should believe that a classical computer cannot simulate your system efficiently. Okay, but quantum computing is an interdisciplinary field, and sometimes the people want to just cut out complexity theory and just say, well, here's a here's a physics reason why my system is hard to simulate. It's hard to simulate just because there's so many states or just because there's so much entanglement. But that's not going to cut it, because there are systems that have lots and lots of states or that have lots of entanglement, but that are nevertheless easy to simulate on a classical computer for some non-trivial reason. Okay, so if you want to know that your system is hard to simulate with a classical computer, then the main tool that we have for that kind of question is complexity theory, reductions, black box lower bounds, things like that. So that's a lot of what I'll be talking about today. Okay, so these principles sort of motivate a technical question, which is the one that I'll mainly focus on, which is what is the biggest advantage that a quantum computer ever gives you for anything? Okay, if all we care about is demonstrating quantum supremacy, rather than solving some application problem, then you could say all else equal, we might as well try to go for the largest possible separation between quantum complexity and the classical complexity for some problem. So at any rate, let's try to understand that question. Okay, so if we look at sort of the famous examples of problems that admit a large quantum speedup or apparent quantum speedup, such as factoring integers, we find that these problems do give you an exponential speedup compared to the best classical algorithms that are currently known. So for factoring in discrete logarithms, if your input has n bits, the best classical algorithm that we know is some version of the number field sieve, which under some number theory conjecture takes time, which is exponential and roughly the cube root of n. Okay, whereas Shor's algorithm famously solves these problems in polynomial time, particular in time that grows about like n squared. Okay, so that's an exponential gap. If we looked at the general problem of simulating quantum mechanics itself, we would we would see an even bigger exponential gap, like let's say, between O of n and 2 to the n, roughly, as far as anyone knows. Okay, but of course, a problem with all of those sorts of speedups is that, they are only conjectural, right? Because no one can prove that factoring or a discrete log are hard for a classical computer. For that matter, no one can prove that p is not equal to np. Nor can anyone prove that p is not equal to bqp, whatever. So, so all those speedups are conjectural, and partly for that reason, a lot of the research in quantum algorithms and complexity has focused on what we call the black box model. Now the biggest advantage of this model is that we can actually prove stuff about it. We can prove that there are quantum speedups that are, exponential, or in this model, sometimes even more than exponential. And that these speedups are real. The separation is not conditional on any unproved conjecture. Okay, so the basic idea of this model is that we consider an oracle function, f, let's say, that takes n possible inputs and produces m possible outputs. And we compare a classical computer against the quantum computer in terms of how many queries they need to make to this oracle function, f, in order to learn something of interest about it. So a classical query algorithm can just repeatedly pick inputs x and feed them to f and learn f of x. Okay, it has no other way of learning about f than by making these black box queries. A quantum computer can have its state can be a superposition over, a whole bunch of different inputs x, or in fact, over a whole bunch of basis states that look like XAW, as I've written there, and then all the different inputs x can be queried in superposition. So what that means is that each basis state like that gets transformed to one of the form x and a plus f of x and w. Okay, so here again, x is the register that stores the input. A is the answer register that just stores the answer f of x, and f of x has to get exclusive ORed into that answer register because the query transformation needs to be a unitary transformation. Okay, which means it has to be reversible. So that's why we do that exclusive ORing. And then W is what's called the workspace, and that's just as many additional qubits as we like that just don't participate in the query, but just maybe store the result of some previous queries or something like that. Okay, so a quantum query is a unitary transformation that looks like that. That can happen for all the XAWs in superposition. And then in between two queries, you can do any unitary transformation that you want as long as it doesn't depend on f. Okay, so, and then at the end, you measure your quantum state. So you measure some designated qubit, and you expect to see a 1 if f has some property and a 0 if it doesn't have that property. Okay, and so the key point is that in this model, we are only counting the number of queries to f, both quantumly and classically. We're not counting any other computational steps. So this is sort of a rudimentary form of complexity theory, a more information theoretic form, but it often captures what we're interested in, because often we do have some subroutine that computes some function f, and it's sort of hopeless to try to probe its internal structure. So this query complexity model, captures how many steps it would take to learn something just by treating f as a black box. Okay, and it so happens that many of the, in fact, most of the quantum algorithms that we actually know today can be viewed within this black box model. Okay, so so a little more formally, we let P be what we call a promise problem about f. So for example, I promise you that f is either a 1-to-1 function, so it's injective, or else it's a 2-to-1 function. I ask you to decide which is the case by querying f as few times as possible. That problem is called the collision problem. Okay, or I promise you that f is either a periodic function or it's far from any periodic function. I ask you to decide which is the case. Okay, that's another example. So then given any problem like that, we can let Q of P be the bounded error quantum query complexity of P, which means the minimum number of queries made by any quantum algorithm that decides P for every input F satisfying the promise. Okay, now R of P is the bounded error randomized query complexity of P. So that's the same thing, but where we only allow a classical randomized algorithm. Okay, and then one of the central questions of this field is just how do Q of P and R of P relate to each other for various promise problems P that we care about. Okay, so in this language, we can rephrase Shor's algorithm in a way that's sort of closer to what he actually did. Right, I would say that Shor's real result is that he gave a quantum algorithm for the period finding problem. That is, determining whether your function is close to periodic. If it is, determining its period. He gave a quantum algorithm for that problem that makes only O of 1 queries to the function. Okay, amazingly, only a constant number of queries. Whereas one can prove that any randomized algorithm for period finding requires at least about n to the 1/4 queries, where n is the range of the function. Okay, so here you should think of capital N as something that's exponentially large. Right, it's your function could have exponentially many possible inputs. So in that case, we're saying that any classical algorithm to find the period of a black box function, is going to have to query the function an exponential number of times. Okay, that's not very surprising because until you happen to find two different inputs of your function that lead to the same output, you haven't really distinguished your function from just a random function that has no period. Right, so you haven't really learned anything about what its period might be. So classically, you provably need exponential time for this, whereas quantumly you don't. Now, there's an additional observation which actually has nothing to do with quantum mechanics. It's purely classical, and that is that if you have a fast algorithm for this period finding problem, then you can also factor numbers and calculate discrete logarithms. Okay, and that's that's obvious, at least if you're Peter Shor in 1994. Okay, that there is this reduction. Okay, but the quantum part of Shor's algorithm is really a black box algorithm for period finding. Okay, and it achieves this huge provable separation. Now that doesn't mean that that there's not a fast. There can't be a fast classical factoring algorithm, right? Of course, no one has proven that, but it does mean that if you were to factor a number in this specific way by reducing it to period finding, then provably you would need exponential time to do it. Okay, so in light of these sorts of speedups, Berman et al. In 2001 asked a question that I think grew on me over time. I think it's a really beautiful question. They ask, is the speedup from Shor's period finding algorithm actually the best quantum speedup possible? You could get even greedier, like a Rumpelstiltskin, right? You could ask, is there some property of n-bit strings that took only, let's say, a constant number of queries to decide quantumly, but a linear number to decide classically? And what's interesting is, if you look through all the examples of quantum algorithms that we know, none of them give you that. Okay, so Shor's problem, as we saw, gives you a constant versus about n to the 1/4 speed up. Simon's problem, which is something that predated Shor's problem, it's like also period finding, but over the group Z2 to the n. That one has a quantum algorithm that takes about log of n queries, whereas any classical algorithm takes about square root of n queries. Okay, where again n is the size of the range of f, the number of inputs different inputs that f has. Okay, so again, there's an exponential quantum speedup, but the classical query complexity seems to hit the ceiling at square root of n. Okay, and we see that for other examples. There's what's called the glued trees problem of Childs et al. This is a beautiful example where you can use a quantum walk to get an exponential speed up over any classical algorithm. So you have an oracle or a black box function that sort of encodes the neighborhood relation of an exponentially large graph that looks like the one in the slide. So it has an entrance vertex and an exit vertex. Each one is connected to a binary tree with, say, 2 to the n children, and the leaves of the 2 trees are connected by a random cycle. Okay, and so you have an oracle that, just given the label of any vertex, tells you the labels of the neighboring vertices, and you also know the label of the entrance vertex. And now your goal is to find the label of the exit vertex. Okay, now one can prove, again, that any classical algorithm for finding the exit vertex is basically just going to get stuck wandering around the middle part of the graph for an exponential amount of time, for about square root of n steps, where here n, capital N, is the total number of vertices. Okay, whereas Childs et al. Showed that if you take a quantum walk on this graph, then the entire cycle in the middle is seen as just like a barrier that is tunneled through, and you will reach the exit vertex after only polylog of big N steps with a good probability. Okay, so by the way, this is another application of a quantum computer. If you're ever lost in a maze that looks exactly like that one, and you could put yourself in superposition, then you can get out of it faster than if you can't.
Scott,
yeah.
we have a
yes.
question.
Yes, please.
So there's a question that, is there an intuition for this lower bound? Like, is this something based on birthday paradox or something?
Yes, that's actually that's basically exactly it. It's in fact, in both cases, for different reasons, it's the birthday paradox, right? So one can show that these so basically you can sort of construct a tree and of all the vertices that you've seen so far, and and until you visited about square root of n vertices, you with high probability you will not have seen any cycle. Okay, and if you haven't seen any cycle, then it's just then you sort of haven't learned anything relevant to where the exit vertex might be. That's sort of how the proof works. But no, my student, Shalev Ben David, actually managed to show that square root of n is also an upper bound for the query complexity of this glued trees problem. Okay, for Simon's problem, it is also easy to see that square root of n is an upper bound, again, because of the birthday paradox.
Maybe it's worth saying that the n to the 1/4 is because of the way you define the problem. The period is square root n.
That's correct. That's right. Thank you, Odette. Yeah. So okay. Now, for if we ask about so now everything I talked about was a total Boolean. Sorry, was a partial Boolean functions or promise problems, right? Problems where you're promised that your function is periodic, or it satisfies the Simon promise, or it is a maze that looks like 2 glued trees. Okay. Now, if we consider problems that lack a promise. Like I give you a bunch of input bits. I ask you to compute their or compute their parity, or compute their majority, or compute some other Boolean function of the input bits. For that kind of problem, in some sense, the situation for quantum speedups is even worse, because there is a famous result from 1998 due to Beals, Berman, Cleve, Mosca, and DeWolf, which says that for these problems, the quantum query complexity is always at least the classical deterministic query complexity to the 1/6 power. Okay, so for total Boolean functions, quantum can at best give you a polynomial speedup. More recently, Andres Ambayanis and I proved that for functions that have permutation symmetry among the inputs and outputs, like the collision problem, 1-to-1 versus 2-to-1, or the element distinctness problem, things like that. For those, the best possible quantum speedup over a classical randomized algorithm is by the 7th power. Okay, so for those, if you don't have enough structure in your problem, sometimes, then we know that only in the query complexity model, only a polynomial quantum speedup is possible. Okay, and of course we do have examples that give you polynomial speedups in those cases. The most famous one being Grover's algorithm. Grover's algorithm searches a list of n elements in only about square root of n steps. Okay, so recently, in the last stock, Andres Ambinas and I had a paper where we did a few things. One of them is that we gave a function that has the largest quantum speedup, yet known, in the black box model. Okay, so we study a problem called the Elation problem. And we show that it has a quantum query complexity of 1. Okay, 1 query. It's hard to do better than that. There's not much you can do with 0 quantum queries. Well, you can compute the constant function. Whereas the classical randomized query complexity we showed is almost a square root of n. Okay. Now the second thing that we showed is that in some sense this is the largest quantum speedup possible. Okay, in the sense that if you take any promise problem, any partial Boolean function p, if it has a quantum query complexity of at most t, and it has n input bits, then it also has a randomized query complexity, which is at most about n to the 1 minus 1 over 2t. Okay, so for example, any function that you could evaluate with 1 quantum query, you can also evaluate with square root of n classical queries. Okay, anything that you can do with 2 quantum queries, you can also do with n to the 3/4 classical queries, and so on. Okay, so this actually resolves this Berman et al. Speedup question in the negative. Okay, it shows that there is no partial Boolean function with a constant versus linear quantum classical gap. You may be able to get arbitrarily close to that, and in fact we conjecture, we haven't proven it yet, that you can get arbitrarily close to that, constant versus linear, but you can't quite achieve, or you may be able to get log of n versus linear. Okay, but at any rate you can't get constant versus linear. And if you restrict to things that you could do with 1 quantum query, then all of them can be done with square root of n classical queries. And in that sense, this Elation, is showing you an optimal speedup, or it's sort of an optimal separation between quantum and classical computing. Okay, so without further ado, let me tell you what the Elation problem is. Okay, so you're given black box access to 2 Boolean functions, f and g. Okay, so the input you should think of as being the truth tables of these functions. So the size of the input is actually well, 2 to the little n plus 1. Okay, so I'll call that a capital N. Okay, I don't actually, I guess what I wrote is off by a factor of 2. Okay, but in any case, the number of input bits is proportional to 2 to the little n. Okay, and now there's some measure that I call phi. Okay, which what it does is it measures the amount of correlation between f and the Fourier transform of g. Okay, hence Elation. So so physicists and mathematicians know other kinds of Fourier transforms, but for theoretical computer scientists, our favorite Fourier transform is the kind that involves a -1 to the x dot y, right? So it takes each basis vector and maps it to a vector of a rescaled vector of 1s and -1s, where whose yth entry, say, is -1 to the x dot y. Okay, so so you can see the definition of this quantity phi, this Elation, which and you can easily prove using Parsifal's identity that this phi is always at most 1 in absolute value. Okay, so to give you some intuition for it, if g is equal to the Fourier transform of f, if g equals the Boolean Fourier transform of f, if g equals f hat, then phi is just 1. Okay, then f and g are maximally correlated. Okay, if f and g are just two random Boolean functions that have nothing to do with each other, then with overwhelming probability, phi will be close to 0. Okay, and so now we can define a promise problem, which is that I promise you that phi is either very large or very small. Let's say either it's at least 0.6 or else say it's at most 0.01 in absolute value. I ask you to decide which of these is the case. Okay, so I actually introduced this problem in 2010 for a different purpose. Namely, this is actually a candidate problem for being a black box problem that is in BQP but not in the polynomial hierarchy. Okay, I was not able to prove that it's not in the polynomial hierarchy, but I still conjecture that, and I think proving that is a wonderful problem in constant depth circuit lower bounds. Now, what Ambianus and I did in our more recent work is that we revisited this problem from a different angle. Okay, we asked, forget about the polynomial hierarchy. Just, how well does this problem do in terms of separating quantum from classical query complexity? And we showed that it gives the maximal gap there. Okay, so in 2010, I observed that this problem is solvable with only one quantum query. And I also proved that it requires at least capital N to the 1/4. So in other words, 2 to the little n over 4 classical queries. Okay, and so recently we were able to improve that bound to about the square root of capital N. Okay, so here's an example of the correlation problem, just to give you some intuition for it. So you can stare at these two functions and ask, are they correlated or are they not? In this case, I believe the answer is that they are correlated. Okay, but it's not certainly not obvious from staring at them. Okay, and more seriously, the point is that being correlated is somehow a very global property of the two truth tables, right? So if you knew the entire truth table of f, then you could solve correlation pretty easily by just querying a few values of g, just seeing, are they, do these values match the Fourier transform or do they not, right? Likewise, if you knew the entire truth table of g, then you could just query a few random values of f, and that would also solve the problem. Okay, but intuitively, if you've only queried a small number of f values and a small number of g values, then they should look pretty random, regardless of whether f and g are correlated or uncorrelated, right? Because even if g is the Fourier transform of f, well, how are you going to notice that? If you've only examined f and g locally, right? You're just going to see what looks like a whole bunch of random 1s and -1s. Okay, so that's the intuition. Of course, that's not the proof of a lower bound. That takes a lot more effort. Okay, so let me tell you why this problem is so easy for a quantum computer. I mean, in some sense, we designed the problem to be maximally easy for a quantum computer. So it's a sort of no great surprise. But here's a trivial quantum algorithm for correlation. Okay, start with n qubits, all in the 0 state. Now apply Hadamard gates to all of those qubits. Okay, that puts them in an equal superposition over all 2 to the n possible strings. Now query f, by which I mean take each basis state x and multiply its amplitude by f of x. Okay, that if you can query f in the way that I showed you before, then it's easy to see that you can also do that so-called phase query. You can make a query that will multiply an amplitude by -1 if f of x is -1 and otherwise do nothing. Okay, so you do that, and then what do you do next? Well, what else? What else do you do with a quantum computer? A Fourier transform, which in this case just means applying another round of Hadamard gates to each qubit. Okay, then you apply g, so you apply a phase query for the function g, and then you do one more round of Hadamard gates on each qubit, and then you measure each qubit. Okay, and then you ask, what is the probability that I have gotten back to the all 0 state? Okay, so you can easily calculate that, and the probability of getting back to the all 0 state is precisely the square of phi. the square of the correlation between f and g. Okay, so you just read off the answer to the problem. It's because that's exactly what the Hadamard gate does in some sense. It affects the Fourier transform on your amplitude vector. Okay, now this was a two-query quantum algorithm. Okay, but if that's too expensive for you, you can even reduce from 2 queries to 1. The way you do that is kind of cute. You can have a control qubit that you put in a superposition, equal superposition of 0 and 1. Then if the control qubit is 0, then you run this algorithm on the slide sort of from the beginning forward. So, apply the H's and then query F, let's say. Whereas if the control qubit is 1, then you run the algorithm backward from the end. So you apply, you Hadamard all the qubits, and then you query G, and then you Hadamard all the qubits again. Okay, now the point is that if F and G were correlated, then the 2 branches of your quantum computation should have led to almost the same state. Which means that if you now measure your control qubit in the plus or minus basis, you ask, is it 0 plus 1 or is it 0 minus 1, then you're always going to see the answer 0 plus 1. Okay, whereas if F and G were not correlated, then these 2 branches of your quantum state are just completely decohered from each other. So when you measure in the your control qubit in the plus minus basis, you see plus half the time and minus half the time. Okay, that's the 1 query quantum algorithm for this problem. Okay, so now the real technical thing that we had to do in our stock paper was how do you prove that the correlation problem requires an exponential in little n number of queries by any classical randomized algorithm, or in other words, square root of big N. Okay, well, I had some, the truth is I had some slides about this, but I took them out because we don't have a lot of time. I will be very happy to talk about the lower bound proof if any of you are interested. But it is a it's an adversary argument. Where you sort of formalize the intuition I was talking about before that says that if you've made only a small number of queries, then with high probability everything that you've seen just looks to you like random bits. So if you were a Bayesian and you had a half prior probability on f and g being completely random Boolean functions and a half prior probability on their being correlated, then your posterior probabilities would still be close to a half. Okay, and in order to prove that, there's sort of only one property of the Fourier transform that gets used, and that's that it is a unitary matrix in which every entry has a small absolute value. Okay, so you could replace the Fourier transform in correlation by any other unitary matrix with the same property, and you would get that same lower bound. Okay, so we actually prove a much more general statement, which you can phrase completely classically if you like, which says that if I have like let's say 2n variables and I know that either they're all completely random or else n of the variables are just biased by a little bit by some sort of uniform unitary transformation that relates them to the other n variables, then it's going to take you a lot of queries to determine which of those is true. And so actually what we do in the proof is that we even though f and g are Boolean functions, we relax them to real valued functions. So we consider a real valued analog of the problem. Okay, we show that proving a lower bound for this real version of the problem implies the same lower bound for the Boolean version. Okay, but then the real version, you're querying a bunch of Gaussian random variables, and then we can start using some linear algebra tools to start studying because a bunch of a product of a bunch of Gaussian variables is still Gaussian, right? And if they're confined to some low-dimensional subspace, like for example, from one function has to be the Fourier transform of the other one, Well, that's still a Gaussian, a multivariate Gaussian, but now just restricted to the subspace. Okay, so we show that a lot of queries are needed to determine whether your multivariate Gaussian lies in this subspace or it doesn't. And for that, there's a lot of a bunch of uses of Azuma's inequality. So we treat the whole the answers to all the queries as a martingale. Anyway, so you can read our paper if you're interested in the details, or ask me about it at the end. Okay, so now the other half of what we proved was efficient classical simulation of k-query quantum algorithms. Okay, so the key to this part of our work was another crucial result of Beals et al. From their paper in 1998. And what they showed there is that if you take any quantum algorithm, call it A, which makes some number of queries to a Boolean input X, let's say T queries, and then you look at the probability that that algorithm accepts, that it outputs yes, as a function of the input X, then that call that P of X. Then P of X is actually a polynomial in X, a multilinear polynomial. Okay, and more than that, the degree of the polynomial is at most twice the number of queries made by the quantum algorithm. Okay, so this is a beautiful connection between quantum query complexity and algebra, and the proof of it is incredibly simple. It's basically just you just stare at what are the amplitudes of your quantum algorithm as a function of the input X. Okay, well initially they're degree 0 polynomials because they don't depend on the input at all. Now each time you make a query, their degree as polynomials increases by at most 1. Okay, and in between two queries you can do a unitary transformation, but that's just linear, so that doesn't increase the degree. And then at the end, you have to square the amplitudes to make them into probabilities. That is what increases the degree from t to 2t. Okay, so so this connection has been used over and over in quantum computing theory. Okay, because what it lets you do is it's that if you want to prove a lower bound on quantum query complexity, prove that there is not an efficient quantum algorithm for some problem, then it suffices to prove a lower bound on the degree of your function, as a polynomial, or sorry, the degree of any polynomial that approximates your function. Okay, so it translates the problem of quantum lower bounds into a problem that's purely mathematical, that has nothing to do with quantum mechanics. Okay, so now our result. Mine and Ambianus's from this year was that if you take any degree k real polynomial, which is bounded for every Boolean input, okay, then there is a classical randomized algorithm that approximates that polynomial to within a small additive error, say epsilon, and that queries a sublinear number of variables. Okay, so there are n variables. It queries only about n to the 1 minus 1 over k of them. So you can estimate any constant degree bounded real polynomial by querying a sublinear number of variables. And in fact, the queries are non-adaptive. Okay, so again, this is a more general statement. It has nothing to do with quantum mechanics in particular, but it certainly implies the thing we want, because you can just take your quantum algorithm, write out its acceptance probability as a polynomial, and then use this sampling algorithm. Okay, and the way that we prove this, we have to sort of do this pre-processing step where we first figure out, are there any inputs to your polynomial that are very, very important, very influential? Okay, if there are, then we split them up. Okay, in order to get rid of the, in order to make the polynomial more balanced, so that all the variables have roughly equal influences. And then after that's been done, then we prove that just the simplest algorithm imaginable works. So what you can do is just take this n to the 1 minus 1 over k variables, pick them at random, just query those, and then just sum all of the monomials that only involve those variables, and use that as an estimate for the rest of the polynomial, and we prove that the variance of that estimator is pretty small. Okay, so
Scott, I have a question.
Yes, please.
So if you did not have this condition that it's bounded in 0, 1, then what would have been the query complexity?
Okay, excellent question. So if it's not bounded, then even we can easily make examples that are hard. Like just take the sum of all the xi's, right? And then it's clearly going to be hard. If you want to know the sum to within plus or minus epsilon, then that's just equivalent to knowing the sum itself, right? So you've got to query all the variables. Maybe a way to think about it is that our algorithm can approximate the polynomial to within whatever is its range on the Boolean inputs times epsilon. Okay, so just for simplicity, I am taking that range to be of size 1. Okay, because that's what it is in the case of quantum algorithms. Because a quantum algorithm, regardless of what it does, it accepts with some probability, which is going to be bounded between 0 and 1, right? Which is often an important fact when you're using this polynomial method. Okay, so we certainly need that boundedness condition. Now, I should tell you that in our original paper, Ambianus and I only proved a weaker result, which was that any block multilinear polynomial, so any degree k polynomial of a very, very special form, could be estimated with a sublinear classical algorithm in this way. But that was enough to imply the desired conclusion about quantum algorithms, because we could improve Beals et al.'s lemma to show that, well, you actually do get a polynomial of this, block multilinear form. Okay, but then we have a more recent paper of Ambianus, a bunch of his colleagues in Latvia, and I, where we study connections between quantum query complexity and growth in Deeks inequality. And one of the things that we do there is that we show that if you've got a bounded polynomial with a bounded low degree polynomial, then you also have a bounded block multilinear low degree polynomial. So the two things are equivalent, and so that implies the result that I've put on this slide. Okay. All right. So let me just say a tiny bit about the function that we conjecture achieves the optimal separation between quantum and classical query complexity for all values of k. Okay, and this is a generalization of the Elation problem to now involve k Boolean functions rather than just 2 of them. Okay, so we call this the k-fold Elation problem. Okay, so you're given Oracle access to k Boolean functions, f1 up to fk, and now we can define this generalized phi, which you can. I'm not going to try to say the formula, but you can read it on the slide. Okay, it's it's a generalization of the Elation. It's what I call a twisted sum, where you've got like a Fourier transform in between every fi and fi plus 1. Okay, and once again, it shouldn't shock you at this point that there is a k-query quantum algorithm to estimate phi. Or to decide whether phi is large or small, promise that one of those is the case. Okay, the algorithm is, well, just go in superposition, query f1, Hadamard all your qubits, query f2, Hadamard all your qubits, query f3, and so on, and then check whether you've gotten back to the all-zero state. Okay, so I mean, if you've spent enough time in quantum computing, then you'll stare at phi, and even though it doesn't involve, say anything about quantum, it looks like a quantum amplitude. So not a coincidence. And once again, one can improve this to a k/2 query quantum algorithm, and the way you do that is you take a control qubit. If it's 0, run the algorithm forward for the first k/2 queries. If the control qubit is 1, run it backward for the last k/2 queries, and then check for interference in the control qubit. Okay, so this problem has an easy k/2 query quantum algorithm. Now, Ambianus and I conjecture that any classical randomized algorithm for k-fold correlation is going to require at least n to the 1 minus 1 over k queries. Okay, so certainly by the result on the last slide, it doesn't require any more than that. Okay, but we conjecture that it does require that number. So in other words, that this problem exhibits the optimal separation between randomized and quantum query complexity for any partial function for the full range of k. Okay, if people are interested, I can talk about the intuition for this conjecture, but basically it's simply that we don't know of any algorithm that's better. And you know, it seems like, you know, the same intuition as for correlation. Until you've made this number of queries, you sort of, you know, you haven't really learned anything to distinguish your functions from just being totally random. Okay, but you know, we are not currently able to prove any lower bound better than square root of big N, or you know, 2 to the little n over 2. Okay, and I regard that as a wonderful open problem. Okay, now a bonus theorem that we prove is that, you know, if k is, you know, the number of Boolean functions is polynomial in little n, you know, and let's say your functions are described, you know, are not black boxes, but are described to you explicitly, say by circuits that compute them, then this is actually a complete problem for quantum computation. Okay, this problem actually captures precisely what you can do in the class BQP. Okay, so that gives you a second sense in which k-fold correlation kind of, I think, captures, you know, what is the maximum possible quantum speedup, we think. Okay, so I want to say a little bit about the situation with total functions. Okay, so remember I said before that Beals et al. Show that for every total Boolean function f, the deterministic query complexity, which we denote by d of f, is at most the bounded error quantum query complexity of f to the 6th power. Okay, and one of my favorite open problems since I started in this field, you know, in the late 90s, was just what is with that 6? Right? Is that really the best separation? You know, can you get a tighter relationship? And you know, until, you know, the long-standing conjecture that, you know, that I made, I think that many others shared, was that that 6 should really be a 2. Okay, that the biggest separation is going to be quadratic, and it's simply going to be achieved when f is the OR function because of Grover's algorithm. Okay, that was the biggest separation that we knew, or that, you know, anyone could think of for any non-promise problem. So, you know, any total Boolean function. Okay. You know, for majority and parity and so on, you get no quantum speedup. For OR and various, you know, like read once function combinations of OR and AND, you get a quadratic speedup. And we couldn't imagine anything that would be better than quadratic, because it seems like if your function is total, then Grover's algorithm is basically the only thing you can do. But we know that Grover's algorithm is optimal, right? That you can only, for searching a list or things like that, you can only hope for a quadratic speedup. Okay, so, you know, I was, you know, I returned again and again to this problem of how do you improve that 6 to a 2. Okay, then there was a breakthrough just this summer by, well, you know, the name unbiased has shown up a lot in this talk, but here it is again. What they did, they built on some earlier work by Goose, Patasi, and Watson, which constructed some very, very strange Boolean functions. And you know, and unbiased et al. Realized that you could use similar functions to just slaughter a whole bunch of conjectures that, you know, that we had about what are the largest possible separations between query complexities. So in particular, they constructed an example of a total Boolean function f where d of f grows like q of f to the 4th power. Okay. And you know, they had a bunch of other things like the first separation between 0 error and bounded error, randomized query complexity. But you know, let's just focus on this. They have an f where d of f is q of f to the 4th. Okay, and so that completely, you know, killed this conjecture. But I wrote a blog post sort of you know, trumpeting their achievement. But I pointed out in that post, well, you know, their example still satisfies that R of F is quadratically related to Q of F. So in other words, if you do a fair comparison between quantum and classical, so you allow both of them, bounded error randomness, then the separation was still only quadratic. So I said, okay, so maybe, if we just rephrase the conjecture in that way, that, that there's at most a quadratic separation between R and Q, then maybe that's still true. Well, I have a pretty bad track record with this sort of thing. It took only a couple weeks after that for my student, Shalev Ben David, to refute that conjecture as well. And what he did is he constructed a total Boolean function f, where the randomized query complexity grows like the quantum query complexity to the 2.5th power. Okay, and the basic idea of his construction is that you start with a partial Boolean function that achieves a huge quantum speedup. So, you could use Simon's problem, for example, but, you might as well use the one with the biggest known separation. So that's the forrelation problem. Okay, so he says start with forrelation, and then somehow we need to turn it into a total Boolean function. Okay, so how do we do that? Well, we consider a forrelation of ands of ors. So in other words, in order to get any bit of input to your forrelation problem, you have to compute the and, of n bits. And then in order to get any input bit to that and, you have to compute the or of n bits. So that gives you a problem with n cubed input bits. Okay, but it's still a promise problem, right? Because, you still have, your forrelation at the top has to satisfy a promise. Okay, but now we do something very clever to make it into a total Boolean function. And that's that we take about 10 log n copies of this tree of forrelation of and of or. Okay, and then we consider the output bits of all of those copies. So call them A1, A2, up to A10 log n. Okay, call that a string A, which is O of log n bits long. So now we will take that string to index into a giant array of size n to the 10. Okay, we call that the cheat sheet array. Okay, and then, when you look in the AF cell of that array, what you expect to find is pointers to certificates proving the values of all of the ands of ors in all of these forrelation instances. Okay, and now the reason why we used and of or here is that is a Boolean function that takes n squared queries to evaluate it classically, but it always has certificates which only involve n bits. So if you want to prove the value to someone, you only have to reveal n bits, like 1 bit within each of the ors, or else just all of the bits in one of the ors. Okay, so this marked cell has pointers to all these certificates, which you can check that yes, indeed, these forrelation instances all had these given inputs, and then also you could check these are, it says here are the inputs to the forrelation instances themselves, that's n bits that's providing, and then you can check that satisfies the forrelation promise. Okay, so now if your entire input has that structure, namely that the forrelation instances give you a string A that points to a marked cell which contains certificates proving that the forrelation instances indeed lead to the string A, and satisfy the forrelation promise. If your input looks like that, then your Boolean function evaluates to 1. Otherwise, your Boolean function evaluates to 0. Okay, so in this way, Shalev defines a total Boolean function. Okay, and then what can we say about its query complexity? Well, the quantum query complexity, so, forrelation we saw has, a 1-query quantum algorithm. The and is square root of n queries. The or is square root of n queries. Multiply all of those, you get n queries. Repeat that log of n times. Well, we won't worry about factors of log of n. Okay, then you learn the string A. You look up the AF cell in your cheat sheet array, and then the certificates have, about n squared bits. but you can check the certificates using Grover's algorithm, using Grover to search for anything that disagrees with the certificates, and that again takes about n queries with a quantum computer. Okay, so in that way, you check whether your input has this form with a quantum algorithm that makes about n queries. Whereas classically, what you could prove is that in order to learn anything, searching inside the cheat sheet array is just going to be hopeless because it has size n to the 10. So in order to even get started, you've got to evaluate at least one of these instances of for elation, of and, of or. Okay, but for elation, we saw before, takes about square root of n queries classically, and takes n queries, or takes n queries. Okay, and that doesn't imply that the composition of them has to be the product, but in this case, you could prove that it is the product, which means that any randomized algorithm for this problem needs at least about n to the 2.5 queries. Okay, so you get the first super quadratic separation between these measures for a total Boolean function. Admittedly, not a function that you would expect to arise much in practice, but it proves the point. Okay, so now here's an amazing connection between two different open problems, which Shalev also pointed out. Okay, suppose that Ambianus and I are right that this k-fold correlation problem has a randomized query complexity of n to the 1 minus 1 over k. Okay, then in Shalev's construction, you could simply replace the correlations by k-fold correlations. Just plug that in, and then what that will give you is a problem that still takes only n times k queries quantumly, which if k is constant is just about n queries, but classically it will take arbitrarily close to n cubed queries. So in this case, the separation would improve to cubic. Okay, so so these two problems: what is the largest possible quantum speedup for partial functions? What is the largest possible quantum speedup for total functions? Which previously it seemed completely unrelated to me. We now know to be connected to each other. Okay. Now whether that 3 is really optimal. What is the truth between 3 and 6? I still don't know. I still conjecture that the 6 could be improved at least to a 4. But then between 3 and 4, I'm not going to make a conjecture. So recently, Shalev and I, along with Robin Kothari, have a paper where we sort of generalize Shalev's cheat sheet construction in order to achieve a bunch of other separations in query complexity. One example is that we have a total Boolean function whose quantum query complexity grows like its degree is a polynomial raised to the 4th power. Okay, previously the best separation was like 1.3 power. Okay, so this shows that the polynomial method, this Beals et al. Thing, can be very, very far from giving a tight lower bound. Okay, so I had a part of the talk where I talk about sampling problems, but because I'm out of time, I think that I'm going to skip this part. I can return if people want to ask me about it afterward. So I talk about Fourier sampling, just sampling, from the Fourier spectrum of a given Boolean function, which is a query complexity problem that where you can actually prove that the quantum, if you're willing to talk about a sampling problem like this one, then the quantum classic versus classical gap for that is actually larger than the largest that you could ever achieve for a decision problem. Okay, for this sampling task, the gap really is like constant versus nearly linear. Okay, and this Fourier sampling was actually the inspiration for me to for Alex Arkhipov and I to come up with what's called Boson sampling in 2011, which is sort of a sampling problem that you could do with a very, very rudimentary type of quantum computer, one that uses only linear optics, which again does something which is not particularly useful for anything, but we can give strong evidence that this sort of sampling task would be hard for a classical computer. Okay, and in recent years there have been some experimental realizations of boson sampling so far with up to 6 photons. We hope to scale that to a larger number. There are other proposals now, many of them based on traditional qubit-based quantum computing, for how you could just sample some probability distribution with your quantum computer, which is hard to sample. Takes exponential time to sample classically. And if you're one lesson of the last few years is that if you're willing to talk about these sampling tasks, then it's very, very often easier to get a quantum versus classical separation than if you insist on talking about decision problems. Okay, so in particular, the group of John Martinez at Google, expects to have devices with 40 or 50 qubits within the next several years, and they're trying to figure out what to do with those. And one of the best candidates for what they could do is just a quantum supremacy experiment, which would basically just apply some random quantum circuit to these 40 or 50 qubits, and then just sample the output distribution, and then you could challenge a classical skeptic to sample from that same distribution in any reasonable amount of time. You could also do Fourier sampling this way. Now a difficulty with all of these sort of sampling type tasks is how do you verify that your device is actually solving it? Right, and that will usually be an asymptotically hard problem. But if you have only 40 qubits, then you could do it with a classical computer. You could store the entire quantum state with only maybe 8 terabytes of RAM, and which exists, and you could do a calculation that confirms that your quantum experiment is outputting what look like reasonable samples. Okay, but the quantum experiment would be doing it a lot faster than your classical verification. So you could, in that way, see evidence for a separation for a genuine quantum speedup. So I think in conclusion, there's a tremendous opportunity to sort of demonstrate quantum supremacy with the medium-sized quantum computers that are going to be available in the near future, even things that fall very far short of universal quantum computation. But if we want to avoid another sort of endless quote-unquote D-wave debate, has there been a speed up or hasn't there been, right? Then we're going to have to keep front and center the question of, what can you actually prove about the quantum versus classical separation? On what grounds do we think that classical simulation of this experiment is hard? And so here there's both a need and an opportunity for direct collaboration, I think more so than there's ever been in the past, between the experimentalists, who are building the systems, and theoretical computer scientists, who will be needed to to understand what is and isn't hard to simulate classically. Okay, and so my parting thought is that maybe we should stop obsessing so much about the need for more quantum algorithms, which is something I always hear people talk about, right? But to me, again, for disproving Gil-Kalai and Leonid Levin, or disproving the skeptics of quantum mechanics, just running a random quantum circuit or doing Elation or Fourier sampling, those are already perfectly good quantum algorithms, right? And the real difficulty is how do you get classical hardness results? How do you show that a classical computer can't do the same things? All right, so I'm happy to take questions. So thank you.
Thank you, Scott. Questions?
I've got a small question about the Elation problems.
Yeah, sure.
Based on, you've got a general result that says that you can solve it in big O of square root n, but do you have a explicit algorithm to do that, or I mean?
Yeah. So So in fact, I can tell you in the case of Elation, the algorithm is extremely simple. In fact, it's what inspired our general result that there is such an algorithm for any problem solvable with one quantum query. Okay, so the algorithm for Elation is just pick square root of big N random values of f and query them. Pick square root of big N random values of g and query them. And then use them to form an estimate of phi. Right, so just consider all of the cross terms among the values that you queried. Right, so like for each x and y that you queried, sum up f of x times -1 to the x dot y times g of y for all of those. Okay, and then use that as your empirical estimate for the Elation. that's the algorithm. That's the whole thing. Okay, and then you can prove that works, right? That once you're looking at square root of n entries, then this gives you an estimator with a reasonably small variance.
Scott, is any of that connected to the Aaronson unbiased conjecture and Boolean functions?
So that's okay. So that's another good question. Okay, so one thing that I didn't talk about, which also involves me and Andres, is so we had in our in this paper in 2011 called "The Need for Structure in Quantum Speedups." So we did two things in this paper. One of them was we showed that with any problem with permutation symmetry, quantum you get at most a polynomial speedup in quantum query complexity. Okay, but now the other thing that we did there is that we conjectured that for any Boolean function which is sort of even close to total in some sense, that you're only going to get a polynomial quantum speedup. Okay, so the more careful version is we conjectured that if you take any quantum algorithm that makes t queries to some Boolean input, then there will be a classical randomized algorithm that makes poly of t queries. Okay, that makes only polynomially more queries than the quantum algorithm, and that approximates the quantum algorithm's acceptance probability on most Boolean inputs. Okay, not necessarily on all of them. We know that that's impossible because of for Elation and Simon's and Shor's problem and so on. But at least for most oracles, you should approximate. You should simulate the quantum algorithm. Okay, so now if this conjecture is true, then one thing it would mean is that we cannot hope to separate BPP from BQP relative to a random oracle, okay, which would answer a question of Lance Fortnell from 1998 or so. But what we did in this paper is that we showed that there is just a purely mathematical conjecture about polynomials, which says that basically any bounded low-degree polynomial with a large variance has at least one very influential variable. Like one variable whose influence is at least 1 over poly of the degree. Okay, and that's a very, very natural conjecture about polynomials and influence. And if it's true, then it implies what I said about quantum algorithms. Okay, so this conjecture, I know a bunch of experts on Boolean functions and Fourier analysis have thought about it. It remains open. There are a few connections to what I've talked about here. Like one of them is that I mentioned this recent paper with Ambianus and his collaborators in Latvia, where we showed that in some sense low-degree polynomials are equivalent to block multilinear low-degree polynomials, right? That it's so basically it for any of these questions, it suffices to restrict your attention to these block multilinear polynomials. So now that is also the case for the Aaronson unbiased conjecture. So we now know that it suffices, if you want to prove the Aaronson unbiased conjecture, it suffices to prove it for these block multilinear polynomials. I should say that was independently proven at the same time by Ryan O'Donnell and I forget who else. I think one of his students.
Right. So just to make sure, it's for the Elation polynomial, the issue is the variance is very small, right? That's why you don't get any influential variables.
Yeah. Well, I mean, the conjecture is let's see. Yeah, that's exactly right. That's exactly right. Yeah. So for the Elation, polynomial, in some sense, it's only interesting if I feed it, sort of, 4 related inputs, let's say, right? And
right.
If I feed it, like random inputs, then it's almost always going to be just outputting 0.
Right.
And then, if I want to estimate that polynomial, on a random oracle, then I'm just going to output 0, and I'll almost always be correct.
Great. Yeah.
Mm-hmm.
Thanks.
Sure.
Anyone else?
So I have a question. Can you go back to the slide on polynomial evaluation?
Yeah, absolutely.
I'm still not sure I understand the problem fully there.
This one?
Yeah, this one. So, so the polynomial is given to us. Is that correct? And you do not know what x1 to xn are.
That's right. That's exactly right. I should have said that. You completely know the polynomial p. You only don't know x1 to xn.
Okay, and if you want to do it with fewer than n queries, what you're saying is, I mean, a probable algorithm is just sample a subset of these and then evaluate only those monomials.
Yep.
But there's no guarantee that it should work.
Well,
even though
Go on.
There's no guarantee that it should obviously work, even though the total sum is bounded between 0 and 1. Even though the whole thing is bounded between 0 and 1, there is no reason why the variance of individual monomials is small.
Well, that's the question, right? Is the variance small or not? So what we proved is that as long as the polynomial is reasonably balanced, so like no variable has too large of an influence, then in fact the variance will be small. Okay, if you query this sublinear number of variables that I've shown on the slide, then and you just form an estimate using only those monomials, and with high probability it will be a good estimate. So then all you have to do is you do some pre-processing step to make sure that your polynomial is balanced, and that pre-processing step does create a bunch of new variables. The number of new variables that it creates is like exponential in k times n. Right, so for so as long as k is constant, then it's still only a linear in n, O of n number of new variables. So you still get an estimator that has this query complexity.
And this is the block multilinear polynomial thing.
Yes, that's right. That's right. This is all for block multilinear polynomials. But this new result that we've proven implies that is enough to handle the general case. Any polynomial can be sort of put into block multilinear form.
Okay, great, thanks.
Sure.
Do we have any more questions? Or okay, then maybe we should take this off air now.
Okay, so thanks again, Scott.
Yeah.
Thanks, everyone. And again, a reminder, so 2 weeks from now we have Ilya Westenstein. So we'll see you 2 weeks from now. Thank you.
All right, well thank you for giving me the opportunity. Thank you for listening. Okay.